Section 3.1 was all about this new idea, the derivative of a function that tells you the slope at any point of an original function. And we introduced a very formal definition for how to compute the derivative of a function. That limit as h approaches 0 of f of x plus h minus f of x all over h. That formula, still critically important, is the formal definition of the derivative. And we're going to spend the whole sort of rest of first semester computing derivatives and learning what kinds of problems we can solve when we can find derivatives. Section 3.2 was all about differentiability. The big takeaway from 3.2 is we have to promise to double check that a function is differentiable before we try to take the derivative. Otherwise, we might accidentally find a derivative when none exists. So we're going to combine these two ideas. What does derivative mean? We're going to start to learn what they're good for. We're going to remember that we always have to check to make sure a function is differentiable before we try to take its derivative. That's our setup here. Here's the good news, is that formal definition for how to compute the derivative using a limit, it's still the formal definition of the derivative. But mathematicians, when they find that they have to perform the same procedure over and over again, start to look for patterns so that they can formalize into rules they can use for making their computations go faster. So we're here to talk about, some shorter methods you can use for finding the derivatives of some simpler functions. So our big idea here, derivative is slope. So think about this. The first kind of function we're going to talk about, a sort of a little bit of I'll call it a shortcut for taking a derivative. We've talked about it a little bit. Anytime we think of a function that's linear, and we know derivative is slope, if we can find the slope of that linear function, that slope, that one number, is the derivative. So imagine a constant function, y equals, a or 7 or some number. When you graph it, it's a graph of a constant function is a horizontal line, and the slope of a horizontal line is 0. So ladies and gentlemen, the derivative of any constant is 0. You have an example on your paper. It says if f of x equals 5, imagine graphing it. F prime of x everywhere is 0. No matter what input you give the f prime function, the output is going to be 0. You have one more tool in your tool belt already, a little bit, and that we know that there are other kinds of lines that aren't horizontal. But if we take the derivative of a linear function, the result is going to be one number, the slope. The slope will be a constant, and that gives us our derivative. So building on that idea, we want to imagine how we could use this definition of limit to arrive at other derivative, this limit definition to arrive at other derivative formulas. So imagine going through this process, taking the limit as h approaches 0 to find the derivative of, for example, x squared. I would expand out x plus h squared. I'm going to notice my x squared terms cancel out. I'm going to be able to factor an h from the numerator and denominator to get rid of my divide by 0 problem. And you'll notice this here highlighted in yellow. The only thing sort of left over at the end is 2x. And you can see where that 2x kind of came from. It was 2x times h once I had expanded x plus h squared, but with an h canceled out. Well, what if I tried that with x cubed? I would expand out x plus h cubed, and I would cancel the x cubes with each other, and I'd be able to factor an h out and cancel the h out. And notice the only thing sort of left over behind after we've canceled the h's out is what's highlighted there in yellow, 3x squared. Now, you could go through this process to find the derivative of x to the 4th and x to the 5th. I think x to the 4th is even on this slide, x to the 6th, and I think you would start to notice a pattern. The pattern comes from the result of expanding out some binomial raised to an exponent. Maybe you practiced in Algebra 2 or Precalculus using Pascal's triangle to expand those out. Don't tell anyone, you're not going to need that right now. And we can start to notice this pattern. The derivative of x squared was 2x. The derivative of x cubed was 3x squared. The derivative of x to the 4th was 4x cubed. Do you catch the pattern? How do you take the derivative of a function that's made up of x raised to some exponent? We formalize these results with a rule, I guess, that we call the power rule. So if you want to take the derivative of x raised to an exponent, the derivative with respect to x, of x raised to an exponent, the exponent that you had sort of comes down to the front to multiply, and you still have a power of x, but now the exponent is one number less. So, for example, here we had, if f of x was x squared, f prime of x we said was 2x. See how the 2, it looks like it sort of dropped down to the front, and the new exponent is 1 less than the old exponent. So, we'll do an example. The first example on your paper there. What if f of x is x to the 5th? What's the derivative? F prime is going to be, what's the old exponent is 5, comes down to the front, turns into a multiplier. The new exponent on x is 1 less than the old exponent. 1 less than 5 is 4. So if f of x is x to the 5th, f prime of x is 5x to the 4th. So now the cool thing is that works whether your fraction, anytime we want to take the derivative of x raised to any exponent, the exponent could be negative, it could be a fraction. So check out this next example. What if I want to take the derivative of 1 over x to the 4th? As long as I can write that as x raised to some exponent, I'm going to be able to use the power rule. So our first job is to remember that we can rewrite sort of this reciprocal notation using negative exponents. So 1 over x to the 4th is equivalent to x to the negative 4th. So notice I started with g of x was 1 over x to the 4th. Look here, I'm still labeling the same function g of x because my first job is to take the original function and rewrite it so that it looks like it's going to follow this rule. So it looks like I'm going to have a function that's x raised to some exponent. So if g of x is x to the negative 4th, now I can use the power rule. The old exponent, negative 4, comes down to the front. My new exponent on x is going to be 1 less than the old exponent, and negative 4 subtract 1 makes negative 5. That's how I get g prime of x is negative 4 times x to the negative 5th. If you wanted to, and if you were taking the multiple choice test, you'd probably find that the answer choice was written like this, negative 4 over x to the 5th, which is equivalent to negative 4x to the negative 5th. Even cooler, my exponent on x doesn't have to be even an integer. Recall this notation. H of x is the cube root of x squared. I can rewrite radical expressions using fraction exponents. The index of my radical becomes the denominator of my fraction exponent. Any exponent I have inside there, any power that x is the input is getting raised to, becomes my numerator in the fraction. And I can rewrite, let's just scooch that out of the way. I can rewrite the cube root of x squared as x to the 2/3 power. Once I have my function rewritten in this format, x raised to an exponent, I can use the power rule to take the derivative. So the derivative of x to the 2/3 power is 2/3 times, that's the old exponent comes down to the front, times x raised to the, my new exponent is going to be 1 less than the old exponent. 2/3 take away 1 makes negative 1/3. That's how I get this derivative of h. So here's a cool little problem. We'll talk in a little bit about what it, talk in a couple of days about what it actually means, but we can calculate this result here now. If the volume of a cube is given by v equals s cubed, can you find dv ds when s equals 4 centimeters? So we can talk about the different notation here. Instead of calling my derivative dv ds, I could also call it v prime of s. Well, what's v prime of s? V is, that's a prime up here. v is s raised to the third power. If I want to take the derivative of, I don't have an input of x, my input is s this time, but that's okay. The same power rule will apply. The old exponent is 3. It's going to come down to the front to multiply. My new exponent on my same variable is going to be 1 less. 1 less than 3 is 2. So I now have an expression for v prime of s. It's equal to 3s squared. This is asking me to say, what is v prime of 4? V prime of 4 is going to equal 3 times 4 squared, which is 48. All right, one more quick pattern that we can use. If we ever want to take the derivative of some function of x, like maybe one of those functions of x from the last example, but it's being multiplied by a constant number, some number that you could factor out, it's going to look like a coefficient, our derivative is going to be that coefficient multiplied by the derivative of the function of x. So it's sort of like you can factor out the constant multiple, take the derivative, and then multiply that constant multiple back. So here's an example. If I want to take the derivative of 5x to the 7th, x to the 7th is a function of x, and 5 is a constant multiple. You can imagine a multiplication dot between the 5 and the x to the 7th. So what this rule tells me is that instead of trying to figure out what the derivative of 5x to the 7th is, I can hold the 5 out here for a second, take the derivative of x to the 7th, which I just did in the last, well, learned a rule a second ago that I can use. The derivative with respect to x of x to the 7th is going to be 7x to the 6th, and then multiply that 5 back. So the derivative with respect to x of 5x to the 7th is 5 times 7x to the 6th. The 5 and the 7 can multiply together and give me 35x to the 6th. Here's a little trickier one. If I want to take the derivative with respect to x of 4 divided by 5x cubed, I can use the power rule and this constant multiple rule as long as I can rewrite this function to look like some number times x raised to an exponent. So that takes a little manipulation here, but you can rethink of this function as 4/5 times 1 over x cubed, or 4/5 times x to the negative third. Once you arrive at this spot, we can use the constant multiple rule in conjunction with the power rule. The derivative of 4/5 x to the negative third is going to be the 4/5, that's the constant multiplier, it just sort of hangs out there for a second. The derivative with respect to x of x to the negative third is negative 3 down to the front times x raised to a new exponent, which is 1 less than the old exponent. That's how I get this negative 4, because that's 1 less than negative 3. Now, I'm going to just simplify however I can. Notice on the free response section, you wouldn't actually have to simplify if you didn't want to. But here we'll practice just to make sure we remember our multiplying. 4/5 times negative 3 makes negative 12/5 times x to the negative 4th. So I could write negative 12/5 x to the negative 4th, or I think you'll find on a multiple choice question, if it were simplified, it would be, we would use this probably a positive exponent notation and have negative 12 over 5x to the 4th. But notice on the free response section, either one of these answers would get full credit.